Have you ever looked up at the night sky and wondered what it would take to reach those distant stars? Today, we're going on a journey to answer one of humanity's most thrilling questions. How long would it take us to travel just 1 light year? And here is a question for you. If you could travel 1 light year per second, where in the universe would you go first? Let me know in the comments. I will pin the most creative answer. Now let's begin. Here's something that might blow your mind right from the start. A light year isn't actually a measurement of time. The word year is right there in the name. But a light year measures distance, not duration. Think of it this way. We're measuring how far light travels in the span of 1 Earth year. And light? Well, light doesn't mess around. It moves at approximately 186,000 kilometers per second. That's the same as 300,000 kilometers per second. In the time it takes you to blink, less than half a second, light could travel more than halfway around our entire planet. Let me paint you a picture of just how fast that really is. If you could somehow travel at the speed of light, you'd circle Earth's equator more than 7 times in a single second. 7 complete trips around our world before you could even finish saying, wow! But here's where things get truly staggering. Even at that mind-bending velocity, it takes light an entire year to cover 1 light year of distance. When we do the calculations, 1 light year equals roughly 5.88 trillion kilometers. That's 9.46 trillion kilometers if you prefer the metric system. Now I want you to really sit with that number for a moment, 5.8 trillion kilometers. To put this in perspective that our human brains can actually grasp, imagine you decided to take a road trip. You hop in your car, crank up your favorite playlist, and start driving. If you maintained a constant highway speed of 60 kilometers per hour, never stopping for gas, food, or sleep, it would take you more than 11 million years to travel just 1 light year. That's right, 11 million years of non-stop driving. You'd need to start your journey long before modern humans even existed, back when our ancestors were still figuring out how to make stone tools. But we're not talking about driving cars through space, are we? We're talking about spacecraft, the pinnacle of human engineering and technology. So let's look at what we've actually built and sent out into the cosmos. Right now, as I'm speaking to you, the fastest human-made object ever created is hurtling through space on a date with destiny. Its name? The Parker Solar Probe. This remarkable spacecraft was launched by NASA on August 12, 2018, with one audacious goal: to touch the Sun. Well, not literally touch it, that would be a very short mission, but to fly closer to our star than any spacecraft has ever dared to venture. On December 24, 2024, the Parker Solar Probe achieved something absolutely extraordinary. It reached a top speed of 192.22 kilometers per second. If you're thinking in miles, that's approximately 430,000 miles per hour. Let that sink in. 430,000 miles per hour. At that velocity, you could travel from New York to Los Angeles in less than 6 seconds. You could circumnavigate the entire Earth in about 3.5 minutes. It's faster than anything humanity has ever built before, a true testament to our engineering capabilities and our burning desire to explore. But here's the humbling part, the reality check that brings us back down to Earth, so to speak. Even at this record-breaking, jaw-dropping speed, the fastest anything made by human hands has ever traveled, the Parker Solar Probe is still moving at just 0.064% the speed of light, not even 1/10 of 1%. It's like comparing a snail's pace to a supersonic jet. And if the Parker Solar Probe were to maintain this incredible velocity and head out into interstellar space toward a destination 1 light year away, the journey would take approximately 1,546 years. That's more than 15 centuries. Columbus sailed to the Americas 533 years ago. The Parker Solar Probe would need almost 3 times that duration to cover a single light year. Think about what that means for a moment. If we had launched the Parker Solar Probe toward a star 1 light-year distant back in the year 479, around the time the Western Roman Empire was collapsing, it would only just be arriving now, in our present day. Every major civilization that has risen and fallen since then, every technological advancement from the printing press to the smartphone, every war fought and every peace treaty signed, all of that history would unfold while our little spacecraft slowly made its way through the cosmic void. And here's something else to consider. The Parker Solar Probe wasn't designed for interstellar travel. Its mission is to study the Sun's outer atmosphere, called the corona, to help us understand solar wind and space weather. The incredible speed it achieved was a byproduct of multiple gravity assists from Venus and its close approaches to the Sun itself. It's using our star's immense gravitational pull to slingshot itself faster and faster like a cosmic whip crack. This technique, called a gravity assist or gravitational slingshot, is how we've managed to send spacecraft to the outer reaches of our solar system without requiring impossible amounts of fuel. But what about spacecraft that were actually designed with interstellar space in mind? Let's talk about the Voyager probes, two of the most iconic spacecraft in human history. Voyager 1 and Voyager 2 were launched in 1977. That's 48 years ago as of now, during a rare planetary alignment that occurs only once every 176 years. This alignment allowed both spacecraft to visit multiple planets using gravity assists, picking up speed with each encounter like a cosmic game of pinball. Voyager 1, currently the most distant human-made object from Earth, is traveling at approximately 17 kilometers per second, which translates to about 38,000 miles per hour. That's fast by everyday standards. You could fly from London to Sydney in less than 20 minutes at that speed. But in the grand scheme of interstellar distances, it's practically standing still. At this velocity, Voyager 1 would need approximately 18,000 years to travel 1 light year. 18,000 years. The last ice age ended around 11,700 years ago. Voyager would need longer than that, longer than the entire span of human civilization, from the first agricultural societies to today, to cover a single light year. And you know what's really fascinating? Voyager 1 has already left our solar system. In August of 2012, it crossed the heliopause, the boundary where the solar wind from our Sun gives way to the interstellar medium. The matter and radiation that exist in the space between star systems. It's literally in interstellar space right now, the first human-made object to achieve this milestone. It's out there, beyond the reach of our Sun's influence, drifting through a realm no human technology has ever entered before. Yet despite this incredible achievement, despite traveling for nearly half a century, Voyager 1 has covered only about 0.07% of a light year. After 48 years of continuous motion through space, it hasn't even traveled 1 light day, the distance light covers in 24 hours. Let me give you another frame of reference that really drives this home. The closest star to our solar system, after our own Sun, is called Proxima Centauri. It's part of the Alpha Centauri star system, and it sits at a distance of approximately 4.25 light-years from Earth. At Voyager 1's current speed, it would take roughly 73,000 years to reach Proxima Centauri. That's more than 3 times longer than anatomically modern humans have existed on this planet. If our ancient ancestors had somehow launched Voyager 1 from a cave somewhere during the last ice age, it still wouldn't have arrived yet. We'd still be waiting. That's the scale we're dealing with when we talk about interstellar travel. Now, I know what some of you might be thinking. Okay, but technology improves, right? We're always building faster rockets and better spacecraft. Surely we can do better than Voyager. And you're absolutely correct to think that way. That's exactly the kind of forward-thinking optimism that drives space exploration. But here's where we need to have an honest conversation about the physics involved and the engineering challenges that stand between us and the stars, because it turns out that going faster in space isn't just a matter of building bigger engines or carrying more fuel. The realities of rocket propulsion are far more complicated and, frankly, far more limiting than most people realize. Every rocket we've ever built operates on a principle discovered by Sir Isaac Newton more than 300 years ago. For every action, there's an equal and opposite reaction. When a rocket shoots exhaust out of its engines at high speed, the spacecraft itself gets pushed in the opposite direction. It's the same principle that makes a balloon fly around the room when you let the air out. Simple in concept, brutally difficult to optimize in practice. The problem is that to go faster, you need more fuel. But fuel has mass, and the more mass your spacecraft has, the more fuel you need to accelerate that mass, which means you need even more fuel, which adds more mass, which requires more fuel. You see the vicious cycle here? This tyranny of the rocket equation, as it's sometimes called, means that conventional chemical rockets have fundamental limitations. Even our most powerful rockets, the ones that can launch massive payloads into orbit or send spacecraft to Mars, can only provide so much velocity change, or what we call delta V in astronautics. To achieve the speeds necessary for practical interstellar travel using chemical rockets alone, you'd need a spacecraft so large, carrying so much fuel, that it becomes physically impractical. We're talking about fuel tanks the size of skyscrapers or even mountains to send a relatively tiny payload on an interstellar journey. And speaking of interstellar, if you're curious about the challenges of traveling within our own solar system, I've actually made a detailed video exploring the absolute limit of human travel through space. It's a fascinating journey in itself, full of surprising complications and clever solutions that engineers have devised. You'll find that link in the description below and on the card above, and I think you'll really enjoy seeing how we navigate even these relatively nearby destinations. But let's get back to our light-year journey, because this is where things get really interesting and where human ingenuity starts to shine. Scientists and engineers around the world have recognized these limitations of chemical propulsion, and they're developing alternative methods that could potentially revolutionize how we travel through space. One of the most promising concepts involves ion propulsion, sometimes called electric propulsion. Instead of burning chemical fuel, ion engines use electricity, typically from solar panels or nuclear reactors, to accelerate charged particles to extremely high velocities. These engines produce much less thrust than chemical rockets. In fact, the acceleration is so gentle you could barely feel it if you were standing next to one on Earth. But here's the beautiful thing. Ion engines can run continuously for years, even decades, slowly but steadily building up speed over time. NASA's Dawn spacecraft, which explored the asteroids Vesta and Ceres, used ion propulsion. So does the Japanese spacecraft Hayabusa 2, which successfully returned samples from an asteroid back to Earth. These missions have proven that ion drives work beautifully for exploring our solar system. But even with ion propulsion, we're still looking at travel times measured in thousands of years to reach another star. The velocities achieved, while impressive compared to chemical rockets over long durations, still fall far short of what we'd need for practical interstellar missions within a human lifetime. This brings us to more exotic and ambitious propulsion concepts, technologies that currently exist only on drawing boards and in research laboratories, but which could theoretically achieve a significant fraction of light speed. One concept that has captured substantial attention from the scientific community is called nuclear pulse propulsion. The basic idea sounds like something out of science fiction. You detonate nuclear bombs behind your spacecraft and ride the shockwave like a surfer catching a wave. Each explosion pushes you a little faster. Detonate enough bombs in sequence and you could theoretically accelerate to a few % of light speed. This isn't just wild speculation. In the 1950s and 60s, a serious study called Project Orion investigated this concept in detail. Scientists calculated that a large spacecraft powered by nuclear pulse propulsion could reach Alpha Centauri in roughly 130 years, still far too long for a single human lifetime, but getting into the realm where a multi-generational ship becomes conceivable. The project was eventually abandoned, partly due to technical challenges, but mostly because of the Nuclear Test Ban Treaty, which prohibited nuclear explosions in space. But the physics is sound, and some researchers continue to explore variations of this concept. Another fascinating approach involves nuclear fusion, the same process that powers the Sun and other stars. Unlike the fission reactions in current nuclear power plants, which split heavy atoms apart, fusion combines light atoms together, releasing tremendous amounts of energy in the process. A fusion rocket could theoretically achieve exhaust velocities of thousands of kilometers per second, far exceeding anything possible with chemical reactions or even fission. If we could build a reliable fusion drive, and that's a very big if, since we haven't yet achieved sustained, controlled fusion, even in ground-based reactors, we might be able to reach speeds of perhaps 5 to 10% of light speed. At 10% of light speed, that light-year journey would take 10 years. That's starting to approach the realm of feasibility for human missions, at least in terms of duration. But fusion propulsion faces enormous technical hurdles. Despite decades of research and billions of dollars invested, we still haven't created a fusion reactor that produces more energy than it consumes for any sustained period. The conditions required for fusion, temperatures of millions of degrees, immense pressures, perfect confinement of the plasma, are extraordinarily difficult to achieve and maintain. And that's in a laboratory on Earth. Imagine trying to build and operate such a system in the harsh environment of space, where repair and maintenance are nearly impossible. We're making progress. Experimental reactors like ITER in France and the National Ignition Facility in the United States have achieved important milestones, but a practical, reliable, space-worthy fusion drive remains firmly in the future. Then there's antimatter propulsion, perhaps the most powerful energy source theoretically available to us. When matter and antimatter meet, they annihilate each other completely, converting all of their mass directly into energy according to Einstein's famous equation E equals mc squared. The energy density of antimatter is unmatched by any other fuel source we know of. A single kilogram of antimatter combined with a kilogram of normal matter would release as much energy as a 43 megaton bomb, roughly twice the yield of the largest nuclear weapon ever tested. Channel that energy properly and you could theoretically accelerate a spacecraft to speeds approaching a significant fraction of light speed, maybe even 20 or 30%. The catch? Actually, there are multiple catches. First, antimatter doesn't exist naturally anywhere near Earth. We have to create it artificially in particle accelerators, and the process is breathtakingly inefficient and expensive. Current production costs for antimatter are estimated at roughly $62.5 trillion per gram. That's not a typo, trillion with a T. And we'd need kilograms of the stuff for a meaningful interstellar mission. Second, storing antimatter is incredibly challenging. It can't touch any normal matter, or it immediately annihilates. So you need magnetic bottles or other containment systems that can hold it perfectly, indefinitely, with zero failures. Third, even if we solve the production and storage problems, designing an engine that can safely harness antimatter annihilation for propulsion remains a massive engineering challenge. So we've established that our current spacecraft are astonishingly slow by interstellar standards, and even our most advanced theoretical propulsion systems face daunting obstacles. But what if we're thinking about this problem all wrong? What if, instead of trying to carry all our fuel with us, we could push spacecraft from Earth, or even from space near Earth, using beamed energy? This is where things get genuinely exciting, because this approach sidesteps many of the fundamental limitations we've been discussing. Enter one of the most ambitious projects ever conceived, Breakthrough Starshot. Announced in April of 2016 by physicist and entrepreneur Yuri Milner, along with renowned physicist Stephen Hawking and Facebook founder Mark Zuckerberg, Breakthrough Starshot aims to send tiny spacecraft to Alpha Centauri within our lifetimes. Not in thousands of years, not in centuries, but in approximately 20 to 30 years after launch. The concept is both brilliantly simple and extraordinarily complex. Take a very small spacecraft. We're talking about something the size of a postage stamp, weighing just a few grams. Attach it to an incredibly thin, reflective sail, and then blast it with powerful lasers from Earth. The photons from the lasers bounce off the sail, transferring momentum and accelerating the craft. Keep the lasers focused on the sail for several minutes, and you could theoretically accelerate this tiny probe to 20% of the speed of light. 20% of light speed. Let that sink in for a moment. At that velocity, our 1 light-year journey would take just 5 years. The trip to Alpha Centauri, 4.25 light-years away, would take roughly 20 years, plus another 4 years for the radio signals, carrying data and images to travel back to Earth. Within a single human lifetime, we could send a probe to another star system and receive information back about what it found there. This would be absolutely revolutionary, a paradigm shift in how we explore the universe. But let's break down what Breakthrough Starshot actually proposes, because the engineering challenges are immense, some might say borderline impossible with current technology. First, the spacecraft itself, nicknamed a Starship, needs to be miniaturized to an extreme degree. We're talking about packing cameras, computers, power systems, communication equipment, and scientific instruments into something that weighs less than a chocolate bar. This requires leveraging advances in nanotechnology, microelectronics, and materials science that are only now becoming feasible. The entire electronics industry's push towards smaller, more efficient chips, driven by smartphones, computers, and other consumer devices, is actually helping make this concept possible. Then there's the sail, often called a light sail or solar sail. This needs to be incredibly lightweight, yet strong enough to withstand the intense laser bombardment and the stresses of acceleration. The sail proposed for Starshot would be just a few hundred atoms thick, made of highly reflective material, and measure about 4 meters by 4 meters, roughly 13 feet on each side. At full acceleration, this sail would experience forces that would tear apart most materials. It would also heat up tremendously as it absorbs even a tiny fraction of the laser energy. Material scientists are exploring various options, including specialized polymers and metamaterials designed specifically for this application. But creating a sail that can survive the journey remains one of the project's greatest challenges. Now here's where things get really ambitious: the laser array itself. To accelerate a tiny spacecraft to 20% of light speed in just a few minutes, you need an absolutely staggering amount of power focused with incredible precision. Breakthrough. Starshot envisions a ground-based laser array consisting of thousands of individual lasers working together in perfect synchronization, producing a combined power output of roughly 100 gigawatts. To put that in perspective, that's approximately 100 times the electrical output of a typical nuclear power plant, or enough to power tens of millions of homes. This array would only fire for a few minutes per launch, but during that time, it would be one of the most powerful directed energy systems on the planet. Each individual laser in this array would need to be powerful yet affordable. Current laser technology costs are still too high for a project of this scale, but researchers are betting on continued improvements and cost reductions, much like we've seen with solar panels and LED lights over the past few decades. The proposal assumes we'll eventually achieve laser costs around 1 cent per watt, which would make the system economically feasible, though still tremendously expensive. Estimates put the total project cost at around $5 to $10 billion. That's expensive, certainly, but comparable to other major space missions and scientific facilities like the Large Hadron Collider or the James Webb Space Telescope. But generating the power is only part of the challenge. Keeping thousands of lasers perfectly synchronized and focused on a target the size of a book that's accelerating away from Earth at increasing velocities requires adaptive optics and control systems of extraordinary sophistication. Earth's atmosphere distorts and scatters light, which is why stars twinkle. The technical term is atmospheric seeing. The same phenomenon that makes stargazing beautiful also makes it incredibly difficult to maintain a tightly focused laser beam through the atmosphere. Astronomers deal with this problem using adaptive optic systems that can adjust their mirrors hundreds or thousands of times per second to compensate for atmospheric turbulence. The Starshot laser array would need similar systems but scaled up massively. There's also the question of what happens when you send something accelerating to 20% of light speed through space. Space, as we often say, isn't really empty. It's a better vacuum than anything we can create on Earth, but it still contains particles, atoms of hydrogen and helium, cosmic dust, charged particles from the solar wind, and cosmic rays. At normal spacecraft speeds, these particles are mostly harmless, but at 20% of light speed, even a collision with a single atom becomes potentially catastrophic. The kinetic energy involved transforms each tiny particle into a high-energy projectile. Hitting a dust grain at that speed would be like being struck by a bullet. Engineers are exploring various solutions to this problem. One approach involves designing the star chip to be as small as possible, minimizing the cross-section and thus the probability of collision. Another involves incorporating redundancy, sending not just one probe but hundreds or even thousands, accepting that many will be lost to collisions but betting that enough will survive to complete the mission. Some researchers are investigating whether the sail itself could provide some shielding, or whether we might develop some kind of electromagnetic deflector that could push charged particles out of the way. All of these solutions add complexity and mass, which works against the fundamental requirement to keep everything as light as possible. Assuming the probe survives the journey and reaches its destination, it then faces another enormous challenge: communication. At a distance of 4.25 light-years, the star chip would be roughly 40 trillion kilometers from Earth. That's 40 followed by 12 zeros. Radio signals follow the inverse square law, meaning they spread out and weaken as they travel. By the time a signal from our tiny probe reached Earth, it would be almost unimaginably faint. To detect it at all would require some of the most sensitive radio telescopes we have, listening intently for the whisper of data crossing the interstellar void. The probe's transmitter would need to be precisely aimed at Earth. Not an easy task when you're traveling at relativistic speeds and can't carry much in the way of attitude control systems. The data rate would be extremely slow, perhaps just a few bits per second at best. After traveling for 2 decades to reach Alpha Centauri, it might take months or even years to transmit back all the data collected. Every single bit of information, each pixel of an image, each measurement from a scientific instrument would be precious beyond measure, representing humanity's first close-up look at another star system. And we need to talk about navigation and targeting. Launching the probe is one thing, but making sure it actually goes where we want it to go is another challenge entirely. At 20% of light speed, the probe will cover the distance from Earth to the Moon, roughly 384,000 kilometers, in about 6.5 seconds. In that time, there's essentially no way to adjust its course. Whatever trajectory it's on when the lasers stop firing is the trajectory it will maintain for the entire 20-year journey. If the aim is off by even a tiny fraction of a degree, the probe could miss Alpha Centauri by billions of kilometers. The target itself presents complications. Alpha Centauri is actually a triple star system consisting of Alpha Centauri, A and B, 2 sun-like stars orbiting each other, plus Proxima Centauri, a small red dwarf that orbits the pair at a great distance. Proxima Centauri is the closest of the 3 to Earth, and we've recently discovered that it has at least 2 planets, including one in the habitable zone where liquid water could exist. This makes Proxima an incredibly enticing target, but hitting a specific star in a multi-star system from 4 light-years away while traveling at relativistic speeds requires navigation precision that pushes the boundaries of what's possible. Despite these monumental challenges, Breakthrough Starshot represents something profoundly important. It's a serious, scientifically grounded attempt to make interstellar travel a reality within our lifetimes. The project has attracted some of the brightest minds in physics and engineering, and it's spurring research and development in areas that have applications far beyond this single mission. The technologies being developed for starshot, advanced lasers, ultra-lightweight materials, miniaturized electronics, precision optics, could revolutionize everything from Earth-based communications to solar system exploration to defense systems. But let's bring this back to our original question. How long would it take us to travel 1 light year? We've seen that with current technology, using our fastest spacecraft, we're looking at roughly 1,500 years. With advanced ion propulsion, we might cut that down to several centuries. Nuclear pulse propulsion could potentially get us there in perhaps a century or so. Fusion drives, if we can build them, might achieve the journey in a few decades. And laser-pushed light sails, like those proposed by Breakthrough Starshot, could theoretically make the trip in just 5 years, though with the massive caveat that we're talking about tiny, unmanned probes, not spacecraft that could carry humans. This brings us to one of the most profound questions in space exploration. What about human interstellar travel? Everything we've discussed so far has focused on robotic probes, but what would it take to send actual people 1 light year into space and bring them back? This is where the challenges multiply exponentially, because now we're not just talking about propulsion and navigation, we're talking about life support, radiation protection, artificial gravity, psychology, social dynamics, and a host of other factors that make human spaceflight orders of magnitude more complex than robotic missions. Let's start with the most basic requirement: keeping people alive. Humans need air to breathe, water to drink, food to eat, and protection from the harsh environment of space. On the International Space Station, which orbits just 400 kilometers above Earth's surface, these resources are regularly replenished by cargo spacecraft. For a journey lasting decades, centuries, or even millennia, that's obviously not an option. The spacecraft would need to be entirely self-sufficient, recycling everything with near-perfect efficiency. Every breath exhaled would need to be scrubbed of carbon dioxide and replenished with oxygen. Every drop of water would need to be purified and reused. Food would need to be grown on board, which means taking along a complete ecosystem: plants, probably insects for pollination, soil or hydroponic systems, lighting, temperature control, the works. The International Space Station currently recycles about 93% of its water, which is impressive, but still requires regular resupply to make up the difference. For an interstellar voyage, we'd need to push that to 99.9% or better, maintaining it perfectly for the entire duration of the mission. A single component failure in the life support system could be catastrophic. This is why any serious proposal for human interstellar travel includes massive redundancy, multiple backup systems for every critical function, which of course adds weight, complexity, and cost. Then there's radiation, one of the most insidious dangers of long-duration spaceflight. Here on Earth, we're protected by our planet's magnetic field and atmosphere, which shield us from most cosmic radiation and solar particles. Even astronauts on the International Space Station receive some protection from Earth's magnetic field. But venture out into deep space, and you're exposed to the full brunt of cosmic rays, high-energy particles that stream through the galaxy at nearly the speed of light. These particles can damage DNA, increasing cancer risk, affecting the central nervous system and causing other serious health problems. On a journey lasting years or decades, astronauts would accumulate radiation doses far exceeding anything humans have ever experienced. The Apollo astronauts who went to the Moon were only in deep space for a few days, and they still received radiation doses significantly higher than on Earth or in low Earth orbit. Multiply that exposure by years or decades, and you're looking at radiation levels that would likely be fatal without substantial shielding. But shielding against cosmic rays is extraordinarily difficult. These particles are so energetic that they can penetrate meters of solid material. To provide adequate protection, you'd need either incredibly thick shielding, adding enormous mass to the spacecraft, or some kind of active magnetic shielding that mimics Earth's protective field, a technology we're only beginning to explore. Some scientists have proposed using water or other hydrogen-rich materials as shielding, which has the advantage of serving double duty as both radiation protection and a consumable resource. Others suggest burying the crew quarters deep inside the spacecraft, surrounded by fuel tanks, cargo, and other equipment that can absorb radiation. Still others are investigating pharmaceutical countermeasures, drugs that might help repair radiation damage or protect cells from it. But the bottom line is that we don't yet know how to keep humans safe from cosmic radiation during multi-decade journeys through deep space. This remains one of the major unsolved problems in human space exploration. And we haven't even touched on the psychological and social challenges. Imagine being confined with the same small group of people for years or decades, unable to go outside, unable to speak with anyone else, unable to breathe fresh air or feel wind or see a horizon. Earth would be just another star in the sky, and your destination would still be unimaginably far away. The isolation would be total in a way that's hard for us to comprehend. Antarctic research stations and submarines give us some insight into long-term isolation, but even those have the knowledge that rescue or resupply is possible, that the mission has a definite endpoint, that you can go home. An interstellar crew would have no such comfort. The psychological screening and training for such a mission would need to be extraordinarily rigorous. You'd need people who are not only technically competent but also emotionally stable, socially adaptable, and psychologically resilient in ways that we don't normally test for or train. You'd need a carefully balanced crew dynamic where people can work together effectively, resolve conflicts constructively, and support each other through years of monotony punctuated by moments of crisis. The wrong mix of personalities could lead to conflicts that threaten the entire mission. History is full of examples of expeditions that failed not because of technical problems, but because of human factors, mutinies, feuds, breakdowns in leadership and cooperation. One proposed solution to many of these challenges is the generation ship concept. If the journey is going to take hundreds or thousands of years anyway, why not design the spacecraft as a self-contained world where people live their entire lives, raise children, who will in turn raise their own children, continuing for generation after generation until the distant descendants of the original crew finally arrive at the destination. This idea has captured the imagination of science fiction writers for decades, and it does solve certain problems. You don't need to keep the same people alive for centuries. You don't need suspended animation or any other speculative life extension technology. You just need a big enough ship with a sustainable ecosystem and a viable population. But generation ships introduce their own host of problems. How large a population do you need to avoid genetic bottlenecks and maintain a healthy gene pool over centuries? Geneticists estimate you'd need at least several hundred people, probably more. How do you maintain social cohesion and mission focus across multiple generations? The original crew would have volunteered for the mission, knowing the sacrifice they were making, but their children didn't choose this life, nor their grandchildren, nor any of the subsequent generations. How do you prevent resentment, rebellion, or simply loss of interest in completing the mission? How do you preserve and transmit technical knowledge over centuries, ensuring that the crew arriving at the destination still knows how to operate and maintain all the spacecraft systems? There's also the question of governance. What kind of social and political system would work for a multi-generational spacecraft? Democracy might be challenging when the population is small and everyone knows everyone else, but authoritarian systems have their own risks, especially over long time spans. You'd need laws and procedures for everything from dispute resolution to resource allocation to criminal justice. You'd need education systems, probably some form of economy, social institutions, culture. You're not just building a spacecraft, you're building a complete society that needs to remain functional and stable for longer than most human civilizations have lasted on Earth. Some researchers have proposed an alternative to the generation ship, Suspended animation or hibernation. If we could safely put humans into a state of reduced metabolism for extended periods, slowing aging, reducing the need for food and oxygen, essentially putting people to sleep for the journey, many of the challenges of long-duration spaceflight would become more manageable. A crew in hibernation wouldn't need entertainment, exercise equipment, or large living spaces. They wouldn't experience the psychological strain of decades of isolation. And they wouldn't age normally, meaning the same people who left Earth could be the ones who arrive at the destination. This concept isn't pure fantasy. Many animals on Earth naturally hibernate, entering states where their metabolism drops dramatically, their body temperature falls, and they can survive for months without eating or drinking. Bears, ground squirrels, and certain bats are well-known hibernators. Some species, like the Arctic ground squirrel, can lower their body temperature below freezing without suffering tissue damage. And there are even more extreme examples. Certain tardigrades, microscopic animals, sometimes called water bears, can enter a state called cryptobiosis, where their metabolism essentially stops completely. In this state, they can survive radiation levels thousands of times higher than would kill a human, extreme temperatures, the vacuum of space, and pressures 6 times greater than the deepest ocean trenches. They can remain in this state for years, even decades, and then revive when conditions improve. Could we do something similar with humans? The honest answer is that we don't know yet. Medical science has made some progress in therapeutic hypothermia, deliberately cooling patients to slow their metabolism during certain surgeries or after cardiac arrest. This buys doctors time to work and can improve outcomes. But we're talking about cooling someone by a few degrees for a few hours or maybe days, not inducing a true hibernation state lasting years. The challenges are formidable. Cooling the human body too much causes ice crystals to form in cells, rupturing them and causing irreversible damage. Extended periods of immobility lead to muscle atrophy, bone density loss, and other problems. And we don't fully understand the metabolic pathways that allow natural hibernators to enter and exit their dormant states safely. Still, research continues. The European Space Agency has funded studies investigating whether human hibernation might be possible for Mars missions, which would last months rather than years. Some researchers are studying the molecular mechanisms that allow hibernating animals to protect their tissues from damage. Others are exploring whether we might chemically induce a hibernation-like state without extreme cooling. It's early days, but if we could crack this problem, it would revolutionize not just space travel, but medicine as well. Imagine being able to place trauma victims in temporary hibernation to stabilize them for transport, or putting terminal patients into suspended animation until cures for their diseases are discovered. But let's assume for a moment that we solve all these problems. Let's imagine a future where we have fusion or antimatter drives capable of reaching 10 or 20% of light speed, where we've developed perfect radiation shielding, where we can either keep people in suspended animation or maintain thriving multi-generational communities aboard spacecraft. We still face one more enormous challenge: the sheer scale and cost of building such vessels. We're not talking about spacecraft like the ones we build today. An interstellar ship capable of carrying humans would be less like the International Space Station and more like a small city that happens to be mobile. To give you a sense of scale, consider that the International Space Station masses approximately 420 metric tons, about the weight of 300 cars. It cost roughly $150 billion to build and assemble in orbit, making it the most expensive single object ever constructed. And the ISS can only support a crew of 6 or 7 people for missions lasting months, with regular resupply from Earth. An interstellar generation ship would need to support hundreds or thousands of people for centuries without any resupply. It would need to be orders of magnitude larger and more complex. The mass would likely be measured in millions of tons, possibly tens of millions. The construction cost would dwarf the ISS. We might be talking trillions of dollars, possibly a significant fraction of the entire global economy. Where would we even build such a thing? Certainly not on Earth's surface. the cost of launching millions of tons of material into orbit would be prohibitive. We'd need to mine resources from asteroids or the moon, process them in space, and assemble the ship in orbit using automated factories and construction techniques that don't yet exist. This would require establishing an entire industrial infrastructure in space first, a multi-decade or century-long project in itself. We'd need orbital refineries, manufacturing facilities, shipyards, and construction crews, essentially bootstrapping an off-world economy capable of producing something as complex as an interstellar ship. And here's something most people don't consider. Once you've built this enormously expensive spacecraft, once you've recruited and trained your crew, once you've loaded provisions and fuel and spare parts, once you've solved all the technical challenges and said your goodbyes to Earth, you're launching on a one-way mission. Even if the spacecraft reaches its destination successfully, even if the crew establishes a colony there, those people are never coming home. The energy requirements to turn around and make the return journey would be astronomical, far beyond what's practical, and Earth would have moved on. Decades or centuries would have passed. Everyone the crew knew would be long dead. The entire civilization they left behind would be unrecognizably different. This raises a profound question. Why would we do it? What's the motivation for undertaking such an expensive, dangerous, and ultimately irreversible journey? There are several possible answers. One is simple survival. If something threatens life on Earth, an asteroid impact, climate catastrophe, nuclear war, a deadly pandemic, or some other existential risk, having a backup copy of humanity living on another world would ensure our species survives. Carl Sagan famously wrote about this, calling it putting all our eggs in one basket if we remain confined to Earth. From this perspective, interstellar colonization is an insurance policy for humanity, expensive but potentially invaluable. Another motivation is scientific discovery. The knowledge we'd gain from studying other star systems up close, from finding out whether life exists elsewhere, from understanding how planets form and evolve in different environments, this would advance our understanding of the universe immeasurably. And there are questions that can only be answered by going there in person. Are there planets with liquid water oceans? Do any harbor life, even just microbial life? What resources are available on other worlds? Could humans actually survive there? These questions have profound implications, not just for science, but for philosophy, religion, and our understanding of our place in the cosmos. There's also something deeper, something harder to quantify, but equally powerful: the human drive to explore. Throughout our history, we've ventured into unknown territories, across oceans, over mountains, into deserts and jungles, even to the poles of our planet, often with little practical motivation beyond the desire to see what's there. Because it's there, as mountaineer George Mallory supposedly said when asked why he wanted to climb Mount Everest. That same impulse, that curiosity and yearning to push boundaries and explore frontiers, might be reason enough for some people. And perhaps there's evolutionary wisdom in that impulse. Species that explore, that adapt to new environments, that don't remain confined to a single ecological niche, those species tend to be more resilient and successful over the long term. But let's get practical again and talk about actual plans and proposals for interstellar missions. Over the decades, scientists and engineers have developed numerous conceptual designs for starships, each attempting to solve the challenges we've discussed in different ways. One of the most famous is Project Daedalus, designed by the British Interplanetary Society in the 1970s. Daedalus was conceived as an unmanned probe to Barnard's star, about 6 light-years away. It would use nuclear fusion propulsion, specifically detonating tiny pellets of deuterium and helium-3 in a reaction chamber to produce thrust. The design called for a 2-stage rocket with a total mass of about 54,000 tons, most of which would be fuel. Daedalus could theoretically reach 12% of light speed, making the journey to Barnard's star in about 50 years. That's not fast enough to make human travel practical, but for an unmanned probe, 50 years is conceivable within the working lifetime of the scientists who designed and launched it. The design was never built, partly because obtaining the required helium-3 would be enormously difficult. Helium-3 is rare on Earth but relatively abundant on the Moon and in the atmospheres of gas giant planets. So mining it would require establishing industrial operations on the Moon or sending ships to skim the upper atmospheres of Jupiter or Saturn, major undertakings in themselves. Later, in the early 2000s, another project called Icarus revisited and updated the Daedalus concept using more recent technology and knowledge. Project Icarus explored various fusion propulsion designs and trajectory options, investigating whether we could do better with several more decades of technological progress. The conclusion was cautiously optimistic. Yes, with advances in fusion technology, materials science and spacecraft design, we could probably build something more capable than Daedalus, but all the fundamental challenges remain. We still don't have working fusion rockets. We still need to figure out how to mine and process extraterrestrial resources at the necessary scale. And 50 years is still a very long mission duration, raising questions about maintaining contact and communication, about technological obsolescence, will the computers on board still function after half a century, and about whether the civilization that launches such a probe will still exist to receive its data. Another fascinating concept that's received serious attention is the nuclear pulse propulsion approach known as Project Orion, which we touched on briefly earlier. Orion was actually studied in considerable depth during the late 1950s and early 1960s by a team that included physicist Freeman Dyson. The basic idea sounds absolutely wild. You build a spacecraft with an enormous shock absorber plate at the rear, then you drop nuclear bombs out the back and detonate them. The explosion pushes against the plate and the shock absorbers smooth out the impulse, accelerating the ship forward. Drop another bomb, another explosion, another push. Repeat this process thousands of times, and you can build up tremendous velocity. The physics actually works. Calculations showed that a large Orion-class spacecraft could reach Mars in just a few weeks, and an advanced version designed for interstellar missions could potentially achieve several % of light speed. The specific impulse, a measure of propulsion efficiency, would be far higher than any chemical rocket, and even better than most proposed fusion designs. The design team worked out the engineering in surprising detail: the size and yield of the nuclear charges, the mass of the pusher plate, the design of the shock absorbers, even how to store and handle thousands of nuclear devices aboard the spacecraft. Project Orion was eventually cancelled for several reasons. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear detonations in the atmosphere and in space, which would have made testing Orion impossible without violating international law. There were also concerns about the radioactive fallout from launching such a vehicle from Earth's surface. Each bomb detonated would release radiation into the atmosphere. Environmental and political considerations killed the project, even though the engineering appeared sound. Some advocates of the concept have suggested that a modern Orion could be assembled in orbit using nuclear charges manufactured in space, avoiding the fallout problem, but this would require space-based industrial capabilities we don't yet possess. More recently, researchers have explored a variation called nuclear pulse propulsion using fusion rather than fission bombs. This would theoretically produce less radioactive debris while still providing enormous thrust. Some designs envision using powerful lasers or particle beams to trigger tiny fusion reactions in pellets of fuel, with the expanding plasma directed by magnetic fields to produce thrust. This approach combines aspects of nuclear pulse propulsion with controlled fusion, potentially offering the best of both worlds. But it also combines the technical challenges of both, requiring us to solve problems we haven't yet mastered individually, let alone in combination. Then there's the Bussard ramjet, a concept proposed by physicist Robert Bussard in 1960. This elegant idea attempts to solve the fuel problem in a completely different way. Don't carry fuel at all. Instead, scoop it up as you go. Space isn't empty, remember? The interstellar medium contains roughly 1 hydrogen atom per cubic centimeter. A ramjet would use enormous magnetic fields to funnel this diffuse hydrogen into a fusion reactor, burn it for energy, and expel it as exhaust to produce thrust. As the ship moves faster, it encounters more hydrogen per second, potentially allowing continuous acceleration throughout the journey. It's a beautiful concept in theory. The magnetic scoop would need to be absolutely huge, perhaps thousands of kilometers across, but it would be just a magnetic field, not a physical structure, so it wouldn't add much mass. The ship could keep accelerating for years or decades, potentially reaching very high fractions of light speed. You wouldn't need to carry massive amounts of fuel, solving one of the fundamental problems of the rocket equation. For a while, the Bussard ramjet was considered one of the most promising approaches to interstellar travel. Unfortunately, subsequent analysis revealed serious problems. First, the interstellar medium is much sparser than originally thought, often less than 1 atom per cubic centimeter, and in some regions far less. At those densities, even a scoop thousands of kilometers across wouldn't collect much hydrogen. Second, the hydrogen in the interstellar medium isn't the kind that fuses easily. Most of it is regular hydrogen, a single proton and electron. Fusing regular hydrogen is much harder than fusing deuterium or tritium, requiring higher temperatures and pressures. Third, even if you could fuse it, the energy gained might not be enough to overcome the drag created by the magnetic scoop pushing through the interstellar medium. Some calculations suggest that a Bussard ramjet might actually slow down rather than speed up, acting more like a magnetic brake than a propulsion system. These challenges haven't completely killed the concept. Some researchers have proposed modified ramjet designs that might work better, or hybrid systems that carry some fuel to get up to speed and then switch to ramjet mode once they're moving fast enough. Others have suggested using the ramjet not for propulsion, but for power generation, scooping up hydrogen to fuel reactors that power other systems. But the original vision of a spacecraft that continuously accelerates by feeding on interstellar hydrogen now looks much less feasible than it did in the 1960s. Let's talk about something closer to near-term reality: robotic exploration of nearby space using technologies that actually exist or are in active development. Before we send humans on decades-long journeys to other stars, we'll almost certainly send much smaller, unmanned probes. And before we attempt 1 light-year, we should probably start with shorter interstellar missions, what scientists call interstellar precursor missions. These would venture beyond the edge of our solar system into true interstellar space, studying the properties of the interstellar medium, the structure of the heliosphere boundary, and the nature of space between stars. NASA has studied several concepts for such missions. One proposal, called the Interstellar Probe, would use a combination of gravity assists and advanced propulsion to reach speeds of roughly 70 to 80 kilometers per second, about twice as fast as Voyager. This would allow it to reach the heliopause, the boundary of our solar system, in about 15 years, and to travel as far as 1,000 astronomical units, roughly 1% of a light year, within 50 years. That's still just a tiny fraction of the distance to even the nearest stars, but it would allow us to study regions of space that no spacecraft has ever explored, gathering data that would be invaluable for planning more ambitious missions. Such a mission could answer fundamental questions about the structure of the heliosphere, the boundary where the sun's influence gives way to interstellar space. It could measure the density, composition, and magnetic fields of the local interstellar medium. It could search for evidence of the hypothetical Oort cloud, a vast shell of icy bodies thought to surround the solar system at distances of thousands of astronomical units. And it could serve as a technology demonstrator, testing systems and techniques that might be needed for future interstellar missions. Think of it as a stepping stone, not traveling 1 light year, but traveling far enough to learn what we need to know before attempting that journey. Current spacecraft propulsion isn't sufficient even for these more modest goals, which is why NASA and other space agencies are investing in advanced propulsion research. One promising technology is solar electric propulsion, a more advanced version of the ion drives we discussed earlier. These systems use solar panels to generate electricity, which powers ion thrusters that can operate continuously for years. The Dawn spacecraft, which explored the asteroids Vesta and Ceres, demonstrated this technology beautifully. Its ion engine produced only a fraction of a pound of thrust, so gentle you could hold it back with your hand, but it operated for over 5.5 years of cumulative firing time, providing a total velocity change far exceeding what any chemical rocket could achieve with the same mass of fuel. For missions venturing beyond Jupiter's orbit, where sunlight becomes too weak for solar panels to be effective, researchers are developing nuclear electric propulsion. This combines a small nuclear reactor with electric thrusters. The reactor provides power regardless of how far you are from the sun, enabling missions to the outer solar system and beyond. NASA has been developing a reactor called Kilopower, designed to produce between 1 and 10 kilowatts of electrical power for decades without maintenance. A spacecraft with such a reactor and efficient electric thrusters could maintain continuous acceleration for years, building up impressive velocities, perhaps not enough to reach another star in a human lifetime, but certainly enough to revolutionize solar system exploration and make those interstellar precursor missions feasible. But here's what's really exciting. We're not just dreaming about these technologies anymore, we're building and testing them. NASA's Artemis program, which aims to return humans to the Moon and eventually send them to Mars, is driving development of many technologies that would also be useful for more distant journeys. Advanced life support systems that can recycle air and water with near-perfect efficiency. Radiation shielding using both passive materials and potentially active magnetic fields. Habitats that can support humans for extended periods in deep space. Power systems that can operate reliably far from the sun. Each of these capabilities, developed for Mars missions lasting months or years, brings us incrementally closer to the technologies we'd need for interstellar voyages lasting decades or centuries. The private sector is also making significant contributions. Companies like SpaceX are dramatically reducing the cost of launching mass into orbit with reusable rockets. This matters because any interstellar mission will require launching enormous amounts of material, fuel, equipment, construction supplies into space. If launch costs continue to fall as they have over the past decade, projects that seemed economically impossible become feasible. Blue Origin, founded by Jeff Bezos, is developing heavy-lift rockets and lunar landers with similar goals. And numerous smaller companies are working on specific technologies, advanced propulsion systems, lightweight materials, miniaturized electronics, autonomous robotics for space construction. There's also increasing recognition that international cooperation will be essential for any interstellar mission. The resources and expertise required are simply too great for any single nation to provide. The International Space Station, despite its name, demonstrates that countries can successfully collaborate on major space projects. Nations that are political rivals on Earth, the United States and Russia for example, have worked together in space for decades. China's space program, though currently separate from ISS operations, has expressed interest in international partnerships. India, Japan, and the European Space Agency all have ambitious space programs. If we can channel these diverse national interests toward a common goal, pooling resources and sharing costs, projects that would be impossible for any single country become achievable for humanity as a whole. And here's something that often gets overlooked in discussions about interstellar travel. We're not starting from scratch. Every mission we've flown, every spacecraft we've built, every experiment we've conducted in space has taught us something. The Voyager probes, launched nearly 50 years ago, are still sending data from interstellar space, still teaching us about environments no human has ever experienced. The Parker Solar Probe is revealing secrets about the Sun's corona and solar wind. The James Webb Space Telescope is showing us galaxies forming in the early universe, helping us understand the cosmic environment our spacecraft would travel through. Even missions that failed have provided valuable lessons. Teaching us what doesn't work is just as important as discovering what does. Consider the cumulative knowledge base we've built since the dawn of the space age. In 1961, when Yuri Gagarin became the first human in space, his flight lasted just 108 minutes, less than 2 hours. Today, astronauts routinely spend 6 months aboard the International Space Station, and the record for continuous time in space is 437 days, set by Russian cosmonaut Valery Polyakov. We've learned how to keep humans alive in space for extended periods, how to maintain their health, how to grow food in microgravity, how to repair and maintain complex systems in the harsh environment beyond Earth's atmosphere. We've also learned about the psychological aspects of long-duration spaceflight. Russian and Soviet cosmonauts have spent cumulative years aboard space stations. NASA conducted extensive studies of isolation and confinement, including year-long missions to prepare for Mars journeys. The European Space Agency ran a simulation called Mars 500, where 6 crew members spent 520 days in an isolated chamber simulating a Mars mission. These studies have revealed the importance of crew selection, the need for privacy and personal space, the value of communication with Earth, and the challenges of maintaining motivation during long missions. Every lesson learned is a piece of the puzzle, bringing us closer to understanding what it would take to send humans on multi-year or multi-decade journeys. We're also making progress in robotics and artificial intelligence that could be crucial for interstellar missions. Modern spacecraft are far more autonomous than their predecessors. The Mars rovers Spirit, Opportunity, Curiosity, and Perseverance can navigate terrain, select scientific targets, and conduct experiments with minimal human input. The New Horizons spacecraft, which flew past Pluto in 2015, had to execute its entire encounter sequence autonomously because the round-trip communication time to Earth was over 9 hours, far too long for real-time control. For an interstellar mission 1 light-year away, the communication delay would be 2 years. Commands sent from Earth would arrive a year after they were transmitted, and confirmation of receipt would take another year to get back. At those distances, spacecraft must be essentially autonomous, capable of making decisions, solving problems, and conducting science without waiting for instructions from home. Artificial intelligence is advancing rapidly in this direction. Modern AI can recognize patterns, make decisions based on incomplete information, learn from experience, and even exhibit creativity in problem-solving. Future interstellar probes might be equipped with AI systems sophisticated enough to conduct scientific investigations independently, selecting which phenomena to study, adapting their mission plans based on discoveries, even diagnosing and repairing their own systems. This isn't science fiction, it's engineering reality that's getting closer every year. The same machine learning algorithms that power self-driving cars, medical diagnosis systems, and natural language processing could be adapted to enable truly autonomous spacecraft capable of exploring interstellar space without constant human oversight. But let's zoom out for a moment and consider the bigger picture. When we ask, how long would it take to travel 1 light year, we're really asking about our place in the universe. We're confronting the vast distances that separate stars, the enormous gulfs of space that seem designed to keep civilizations isolated from one another. The physicist Enrico Fermi famously asked, "Where is everybody?" pointing out that if intelligent life is common in the universe, and if interstellar travel is possible, we should see evidence of other civilizations everywhere. The fact that we don't might suggest that interstellar travel is prohibitively difficult, perhaps even impossible, with the laws of physics as we understand them. This is known as the Fermi paradox, and it's one of the most profound questions in science. There are many proposed solutions. Maybe intelligent life is extremely rare, and we're alone or nearly alone in the galaxy. Maybe civilizations inevitably destroy themselves before achieving interstellar travel. Maybe interstellar travel is possible but so difficult that most civilizations never attempt it. Or maybe alien civilizations are out there, but we haven't recognized their signals or artifacts because they're using technologies or communication methods we can't detect or don't recognize. The distance problem we've been discussing, the fact that even our fastest spacecraft would take millennia to reach another star, might be part of the answer to the Fermi paradox. If every civilization faces the same challenge, if the laws of physics impose the same speed limits on everyone, then interstellar travel might be rare simply because it's so difficult. A civilization might need to be very advanced, very committed, and very lucky to achieve it. And once they do, the timescales involved mean that encounters between civilizations would be extraordinarily rare. A civilization that sent out colony ships thousands of years ago might no longer exist by the time their descendants reach another star. Signals traveling at light speed would take years or decades or centuries to cross the distances between stars, making real-time communication impossible. Yet despite these daunting realities, I find it hard to believe that interstellar travel is impossible. Difficult? Yes. Expensive? Absolutely. Requiring technologies we haven't yet developed and perhaps centuries of continued progress, certainly. But impossible? The universe doesn't seem to work that way. Throughout history, things that seemed impossible became merely difficult, then became routine. Flying was impossible until the Wright brothers made it difficult in 1903. Reaching space was impossible until it became difficult with Sputnik in 1957. Landing on the moon was impossible until Apollo 11 made it reality in 1969. Reusing orbital rockets was considered impractical until SpaceX made it routine in the 2010s. Each breakthrough builds on previous ones, and the pace of progress accelerates. It took humanity thousands of years to progress from basic agriculture to the Industrial Revolution. It took less than 200 years to go from steam engines to nuclear power. Less than 70 years from the first airplane to landing on the moon. Less than 50 years from the first computers filling entire rooms to smartphones with more computing power than existed in the entire world in 1960. If this exponential progress continues, and there's no fundamental reason why it shouldn't, then technologies that seem impossibly advanced today might be commonplace in a century or two. Consider what life was like 100 years ago, in 1926. There was no television, no computers, no antibiotics, no jet aircraft, no nuclear power, no space travel, no internet. Someone from that era, transported to today, would find our world almost unrecognizable, filled with technologies that would seem like magic. Now imagine what life might be like 100 years from now, in 2126. What technologies that we can barely imagine today might be routine then? What problems that seem unsolvable now might have elegant solutions? It's entirely plausible that our descendants will look back at our struggles with interstellar travel the way we look back at early attempts at aviation, crude first steps in mastering a new frontier. There's also the question of whether we're thinking about this problem correctly. We've been focused on physically traveling 1 light year, on building spacecraft and moving mass across interstellar distances. But what if there are other approaches? Some scientists have proposed sending information rather than matter, transmitting the genetic blueprints and accumulated knowledge of humanity to a destination star system where automated systems would synthesize biological organisms and recreate human civilization. This sounds fantastical, but we already have the basic technologies. We can sequence and synthesize DNA. We can store vast amounts of information in digital form. We can create artificial wombs and tissue cultures. Given enough advancement, we might be able to send the information needed to recreate humanity across interstellar distances at the speed of light, then use automated factories and biological synthesis to turn that information into actual people at the destination. This approach, sometimes called digital panspermia, or genetic cargo, would be vastly lighter than sending physical humans. A powerful enough transmitter could beam the information to multiple star systems simultaneously. The time to destination would be measured in years rather than centuries or millennia. 1 light year would take exactly 1 year to transmit at light speed. Of course, this raises profound philosophical and ethical questions. Are the synthesized humans at the destination really us? Is this actually traveling? Or is it more like sending instructions for someone else to create copies of us? What rights do these synthetic humans have? Who decides whether this is ethical? These aren't just technical questions, they're deep philosophical puzzles about identity, consciousness, and what it means to be human. Another speculative but scientifically grounded idea involves taking advantage of relativistic effects. Einstein's theory of relativity tells us that time passes differently for objects moving at different speeds. The closer you approach light speed, the slower time passes for you relative to the outside universe. This is called time dilation, and it's been experimentally verified countless times. At 90% of light speed, time aboard your spacecraft would pass at about 43% the rate of time on Earth. At 99% of light speed, it drops to about 14%. At 99.9%, just 3.5%. This means that from the perspective of the travelers, the journey becomes much shorter. A trip that takes 100 years according to Earth clocks might feel like only 3.5 years to the crew traveling at 99.9% of light speed. They'd arrive at their destination having aged only a few years, while a century would have passed on Earth. This doesn't violate the light speed limit. Light itself still takes 100 years to make the journey, but it does offer a potential solution to the human lifespan problem. If we could build spacecraft capable of reaching ultra-relativistic speeds, the travelers could visit distant stars within their natural lifetimes, even though centuries pass for the rest of the universe. The catch, of course, is that reaching these extreme velocities requires absolutely staggering amounts of energy. The faster you go, the more energy it takes to go even faster. This relationship isn't linear, but exponential. Accelerating a spacecraft to 99.9% of light speed would require energy equivalent to many times the total annual energy production of our entire civilization. And you'd need that energy again to slow down at your destination, assuming you want to actually stop and explore rather than just flash past at near light speed. The engineering challenges of containing, controlling, and directing that much energy are almost beyond comprehension with current technology. But let's imagine just for a moment that we solve all these problems. Let's say that in a few centuries, humanity develops fusion or antimatter propulsion capable of accelerating spacecraft to significant fractions of light speed. We've mastered radiation shielding, developed reliable suspended animation or multi-generational habitats, built AI systems capable of maintaining spacecraft for decades or centuries. We've established space-based industries that can construct enormous vessels without the prohibitive cost of launching everything from Earth's surface. We've solved the social, political, and economic challenges of organizing such missions. What then? Where would we go? What destinations within 1 light year or even several light years would be worth the tremendous effort and resources required to reach them? This is where our growing knowledge of exoplanets becomes absolutely critical. Just 25 years ago, we didn't know with certainty that planets existed around other stars. We suspected they must, but we had no proof. Then in 1995, astronomers Michel Mayor and Didier Queloz discovered the first confirmed exoplanet orbiting a Sun-like star, a Jupiter-sized world orbiting impossibly close to its star, nothing like any planet in our solar system. This discovery revolutionized astronomy and earned Mayor and Queloz the Nobel Prize in 2019. Since then, the floodgates have opened. NASA's Kepler Space Telescope, launched in 2009, discovered thousands of exoplanets by watching for the tiny dimming of starlight that occurs when a planet passes in front of its star. The Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, is continuing this work, surveying even more stars. The The James Webb Space Telescope, operational since 2022, is beginning to analyze the atmospheres of some of these worlds, searching for the chemical signatures that might indicate life. We now know that planets are common. There are likely more planets than stars in our galaxy, with hundreds of billions of worlds waiting to be discovered and explored. Some of these exoplanets are truly extraordinary. We've found hot Jupiters orbiting so close to their stars that their surfaces are molten. We've discovered super-Earths, rocky planets larger than Earth but smaller than Neptune. We've identified planets in the habitable zones of their stars, the orbital distances where temperatures might allow liquid water to exist on the surface. We've even detected a few planets with chemical composition suggesting they might be covered in deep oceans. And remember, we've only examined a tiny fraction of the stars in our galaxy. There are likely millions of potentially habitable worlds within a few thousand light-years of Earth, and probably many more beyond. Now here's the exciting part. The closest star system to us, Alpha Centauri, actually has planets. Proxima Centauri, the nearest of the three stars, has at least 2 confirmed planets. One of them, Proxima Centauri b, orbits in the habitable zone. It's a rocky planet with a mass about 1.2 times that of Earth, orbiting at just the right distance for liquid water to potentially exist. It completes an orbit around its star every 11.2 days, which sounds incredibly fast until you remember that Proxima Centauri is a red dwarf, much smaller and dimmer than our Sun, so planets need to orbit close to receive enough warmth. Is Proxima b actually habitable? We don't know yet. Red dwarf stars produce powerful flares that could strip away a planet's atmosphere or irradiate its surface. The planet is probably tidally locked, meaning one side always faces the star while the other remains in perpetual darkness, which could create extreme temperature differences. We don't know if it has a magnetic field to protect against stellar radiation or an atmosphere thick enough to distribute heat from the day side to the night side, but the mere fact that there's a potentially habitable world at the nearest star system, just 4.25 light-years away, is tantalizing. If we're going to attempt interstellar travel, Proxima b is perhaps the most obvious first destination. This brings us back to Breakthrough Starshot, which specifically targets the Alpha Centauri system. If those tiny light sail probes successfully reach Proxima Centauri at 20% of light speed, taking 20 years to arrive, what might they discover? They could photograph Proxima b up close, determining whether it has oceans, continents, ice caps, clouds. They could analyze its atmosphere, if it has one, looking for oxygen, methane, water vapor, and other gases that might indicate biological activity. They could measure its magnetic field, study its geology, search for auroras or volcanic activity. Even if the probes only have a few hours to collect data as they flash past the planet at relativistic speeds, the information returned would be worth more than everything we've learned about exoplanets from distant observations. And if Proxima b turns out to be genuinely habitable, with liquid water, a stable atmosphere, and no deal-breaking hazards, it would immediately become the primary target for humanity's first interstellar mission. A journey of 4.25 light-years is still incredibly daunting, still far beyond our current capabilities, but it's manageable in a way that journeys of dozens or hundreds of light-years are not. A fusion-powered spacecraft traveling at 10% of light speed would reach Proxima Centauri in about 42 years. That's a long time, but it's within the realm of a single human lifespan, especially if we develop life extension technologies or suspended animation. A multi-generational ship would only need to support 2 or 3 generations rather than dozens. There are other nearby targets worth considering as well. Barnard's star, about 6 light-years away, is another red dwarf that might have planets. We haven't confirmed any yet, but the search continues. Sirius, the brightest star in our night sky, is 8.6 light-years away, much farther than Proxima, but it's a spectacular binary system with a white main sequence star and a white dwarf companion, offering unique scientific opportunities. Tau Ceti, just under 12 light-years distant, is similar to our Sun and has at least 4 confirmed planets, possibly more. Each of these systems represents a potential destination, a place where humanity might one day plant its flag on another world. But here's what really captures my imagination. We're living in the time when we'll make these decisions. Within your lifetime, yes, yours, the person reading this, humanity will likely confirm whether life exists on worlds around other stars. The James Webb Space Telescope and its successors will analyze exoplanet atmospheres with unprecedented precision. Future space-based telescopes are already being designed specifically to directly image Earth-like planets around nearby stars, to see them as actual points of light rather than just statistical blips in stellar brightness curves. We might capture images of clouds swirling over alien oceans, seasons changing on distant continents, the unmistakable signature of chlorophyll or some other photosynthetic pigment. We might find life, actual alien life, within the next few decades. And if we do, everything changes. The question shifts from, should we attempt interstellar travel, to how soon can we get there? And the discovery of life elsewhere, even just microbial life, would be the most profound scientific discovery in human history. It would answer one of our deepest questions: are we alone? And if the answer is no, if life exists out there, then suddenly the enormous cost and difficulty of interstellar travel becomes worthwhile in a way that purely exploratory missions might not be. We would have a destination not just in space but in significance, a place where we could study alien biology, where we might find answers to questions about the origins and nature of life itself. Even if we don't find life, the exploration of other star systems would teach us things we can barely imagine. Every star system is different, shaped by unique conditions during its formation. Some stars have planets with compositions nothing like anything in our solar system. We've discovered worlds made mostly of carbon, potentially covered in diamond and graphite. We've found planets where it rains glass sideways in howling winds. We've identified systems with multiple gas giants orbiting closer to their stars than Mercury orbits our Sun. Each of these bizarre environments tells us something about planetary formation, stellar evolution, and the incredible diversity of the universe. By exploring beyond our solar system, we'd also gain a cosmic perspective that's impossible to achieve by staying home. From Earth, or even from Mars or the outer planets, we can study the universe through telescopes, but we're always looking at ancient light, at things as they were years, centuries, or millions of years ago. By going there in person, or sending sophisticated probes that can explore in real time, we'd experience other star systems directly, understanding them in ways that remote observation can never provide. We'd learn whether our theories of planetary science, developed by studying just one star system, apply universally, or whether each system requires its own explanations. There's also tremendous practical value in learning how to travel between stars, beyond the obvious scientific benefits. The technologies developed for interstellar missions would have countless applications closer to home. Advanced propulsion systems would revolutionize travel within our solar system, making missions to the outer planets routine rather than once-in-a-generation events. Improved life support and recycling systems would benefit not just spacecraft, but communities on Earth dealing with resource scarcity. Radiation shielding technology would protect not only astronauts, but also people on Earth from solar storms and cosmic rays. Autonomous AI systems developed for spacecraft could tackle complex problems in medicine, climate science, resource management, and countless other fields. And there's something deeper, something about the human spirit that makes exploration worthwhile for its own sake. We are a species that looks to the horizon and wonders what lies beyond. We've always been explorers, from our earliest ancestors who left Africa to populate the globe, to the Polynesians who settled remote Pacific islands using nothing but outrigger canoes and their knowledge of stars and currents, to the astronauts who first looked back at Earth from the moon. That same drive, that same curiosity, that same refusal to accept that any place is beyond our reach. It's part of what makes us human. Carl Sagan captured this beautifully in his book Pale Blue Dot, reflecting on an image of Earth taken by Voyager 1 from 4 billion miles away, where our entire planet appears as a single pixel, a tiny speck in the vastness of space. He wrote about how that image should humble us, reminding us of our insignificance in the cosmic scale, but also how it should inspire us to protect our fragile world and to reach beyond it. The spacecraft will be encountered, and the record played only if there are advanced spacefaring civilizations in interstellar space. Sagan wrote about the golden record carried by the Voyager probes. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. That hopefulness, that optimism about humanity's future among the stars, persists despite all the challenges we've discussed. Yes, traveling 1 light year with current technology would take 1,500 years. Yes, we face enormous obstacles with propulsion, radiation, life support, cost, and a dozen other factors. Yes, the distances are so vast that they beggar the imagination, making interstellar travel seem almost impossible. But almost impossible is not the same as impossible. And throughout history, we've specialized in achieving things that seemed impossible. Let me put this in perspective by talking about one more crucial factor we haven't fully addressed: time scales and patience. Our species tends to think in very short time frames. A political term is measured in years, a human lifetime is measured in decades. Even our longest-lasting institutions, religions, nations, universities, rarely persist unchanged for more than a few centuries. But the universe operates on vastly longer timescales. Stars burn for billions of years. Galaxies evolve over tens of billions of years. The light we see from distant galaxies left those galaxies when the universe was young, traveled for billions of years through expanding space, and arrived at our telescopes only recently, bringing us news of a cosmos long since transformed. If we're serious about becoming an interstellar species, we need to start thinking on longer timescales. A journey lasting 500 years seems impossibly long from our perspective, but it's barely a moment in cosmic time. If humanity survives and thrives for thousands or millions of years, and there's no fundamental reason we shouldn't, assuming we navigate the various existential risks we face, then missions lasting centuries become perfectly reasonable investments. Our distant descendants might look back on these first interstellar voyages the way we look back on the great voyages of exploration from Earth's age of discovery, when ships took years to circumnavigate the globe, and captains set out knowing they might never return. This long-term thinking is already emerging in some areas of space exploration. The Cathedral Builders project, inspired by the medieval craftsmen who began constructing cathedrals knowing they wouldn't live to see them completed, proposes that we should start building infrastructure for interstellar missions now, even knowing that the missions themselves might not launch for a century or more. Begin developing the technologies, establishing the industrial base in space, training the engineers and scientists, creating the social and political structures needed to sustain multi-generational projects. Each generation contributes what it can, building on the work of previous generations, creating something that will benefit future generations. This approach has historical precedent. The Great Wall of China took centuries to build, with multiple dynasties contributing to its construction. The mathematical and astronomical knowledge needed for modern space travel was accumulated over millennia, with contributions from Babylonian astronomers, Greek geometers, Islamic scholars, European Renaissance scientists, and countless others, each building on the work of their predecessors. The International Space Station, though built over just a few decades, required the accumulated knowledge and technology of the entire space age. An interstellar mission would be a logical extension of this tradition, humanity working together across generations toward a common goal. There's also the question of what constitutes success for an interstellar mission. We tend to think in binary terms. Either we reach the destination or we fail. But there's tremendous value in the attempt itself, regardless of the outcome. The Apollo program's primary goal was to land humans on the moon, but its lasting impact went far beyond those 6 successful landings. It drove technological innovation that gave us everything from integrated circuits to cordless tools. It inspired an entire generation to pursue careers in science and engineering. It demonstrated that humans could accomplish seemingly impossible goals through determination and cooperation. Even if we launch an interstellar mission that never reaches its destination, perhaps it fails due to technical problems, or changes in priorities back on Earth lead to the mission being abandoned, the knowledge gained, the technologies developed, and the inspiration provided would still make it worthwhile. Let me also address something that often comes up in discussions of interstellar travel: the idea that we should fix Earth's problems before we attempt to explore the stars. This is sometimes framed as an either-or choice, as if the resources devoted to space exploration come at the expense of solving poverty, disease, climate change, or other pressing issues. But this is a false dichotomy. The global space industry, including government and commercial activities, represents less than 0.5% of the world's total economic activity. Even an ambitious interstellar program costing hundreds of billions of dollars over many decades would be a tiny fraction of global GDP. We can absolutely address Earth's problems while also pursuing space exploration. In fact, we must do both. Moreover, many of the technologies developed for space have direct applications to Earth's challenges. Solar panels, now crucial for renewable energy, were refined for spacecraft. Water purification systems developed for the International Space Station are being used to provide clean drinking water in developing nations. Satellite technology enables global communications, weather forecasting, GPS navigation, climate monitoring, and countless other services we now take for granted. The same would be true for interstellar technologies. Life support systems that can sustain humans indefinitely with perfect recycling would be invaluable for resource-constrained communities on Earth. Energy systems capable of powering spacecraft for decades could transform how we generate and store power terrestrially. Materials science advances needed for radiation shielding could improve everything from medical equipment to nuclear reactor containment. There's also a philosophical argument. Humanity needs inspiring goals that unite us and give us something to strive toward beyond our immediate survival. The challenge of reaching the stars, of extending our presence beyond our home world, of searching for life elsewhere in the universe, these pursuits tap into something fundamental about human nature. They remind us that we're capable of greatness, that our species can accomplish extraordinary things when we work together. In an age often characterized by division, cynicism, and short-term thinking, the vision of humanity as a spacefaring civilization offers hope and purpose. Now let's bring all of this together and try to answer our original question as completely as possible. How long would it take to travel 1 light year? The answer, like so much in science, is it depends. With current technology, specifically the fastest spacecraft we've ever built, it would take approximately 1,500 years. That's using gravity assists and the most efficient trajectories we know how to calculate with existing propulsion systems. For all practical purposes, it's impossible with what we have today. With advanced ion propulsion running continuously for years, we might reduce that to several centuries. Still far too long for any human crew, but potentially feasible for robotic probes designed to last for extended periods. With nuclear pulse propulsion like Project Orion, or with fusion drives if we can develop them, we might achieve the journey in 50 to 100 years. That's getting into the realm where a human crew might survive the trip with suspended animation, or where a multi-generational ship could make the voyage with only a few generations needed. With antimatter propulsion, if we can ever produce and store antimatter in the necessary quantities, we could potentially reach 1 light year in a decade or two. And with light sail technology like Breakthrough Starshot proposes, tiny unmanned probes could make the journey in approximately 5 years, traveling at 20% of light speed. This is the most promising near-term approach to reaching another star system within a human lifetime, though it requires solving numerous engineering challenges we haven't yet mastered. Each of these approaches has different trade-offs involving mass, cost, complexity, risk, and feasibility, with current or near-future technology. But here's what's really important. The question isn't just about the time it takes to travel 1 light-year with today's technology. It's about how that time frame will change as our capabilities improve. 100 years ago, the idea of reaching orbit was pure fantasy. 50 years ago, landing on the moon seemed impossibly ambitious until we actually did it. 25 years ago, we didn't even know planets existed around other stars. Today, we're seriously discussing missions to those planets, designing spacecraft that might actually reach them, and developing technologies that could make interstellar travel not just possible, but practical. The trajectory of technological progress suggests that what seems impossible today often becomes routine tomorrow. If we maintain our commitment to space exploration, if we continue investing in the necessary research and development, if we think in terms of generations rather than election cycles or quarterly earnings reports, then traveling 1 light year and eventually many light years will become achievable. Not easy, certainly, not cheap, not without risks and setbacks and failures along the way, but achievable. So where does this leave us? Standing at the threshold of something extraordinary. We're the generation that will map the nearby stars, catalogue their planets, and perhaps discover life beyond Earth. We're developing technologies that could, within our lifetimes, send probes to other star systems. We're laying the groundwork for missions that might launch decades from now, but will carry humanity's presence to destinations light years away. And we're learning to think not just in terms of our own lifetimes, but in terms of the multi-generational projects that will define humanity's expansion into the cosmos. The journey of 1 light year represents more than just distance. It represents a fundamental challenge to our species. Can we think beyond immediate gratification? Can we work together across national, cultural, and generational boundaries? Can we commit resources to projects whose benefits we ourselves may never see? Can we maintain focus and determination over timescales measured in decades or centuries? These are questions not just about engineering and physics, but about who we are as a species and who we want to become. I find it profoundly moving that we live in the time when these questions are shifting from philosophical speculation to practical consideration. Our ancestors looked at the stars and created myths and legends to explain them. Our recent ancestors looked at the stars through telescopes and discovered their true nature: distant suns, surrounded by worlds, separated by vast gulfs of space. Now we're looking at the stars and asking not just what are they, but how do we get there? We're no longer content to observe from a distance. We're planning to visit. The challenges are immense. Light years are distances almost beyond human comprehension, representing gulfs of space so vast that our fastest spacecraft would take millennia to cross them. The engineering obstacles, propulsion, energy, life support, radiation protection, navigation, communication would strain even our most optimistic technological projections. The costs would be staggering, requiring resources and commitment on a scale humanity has rarely mustered. And the timeframes involved mean that any interstellar mission would be a gift to future generations, an investment whose returns we ourselves might never see. But we've faced impossible challenges before and overcome them. We've crossed oceans in wooden ships, not knowing what lay beyond the horizon. We've split atoms and harnessed nuclear fire. We've visited other worlds in our solar system and sent our robotic ambassadors into interstellar space. We've mapped the human genome, eradicated diseases, connected the entire world through instant communication. We've done things that would seem like magic to people living just a few generations ago, and we'll continue doing things that seem impossible today. The first mission to travel 1 light year, whether it arrives in 5 years or 500, will mark a turning point in human history. It will be the moment when we cease to be a single planet species confined to our birthplace and become something greater, a civilization that can reach other stars, explore other worlds, and perhaps one day encounter other forms of life. That moment is coming, maybe not this year or next year, maybe not in this decade or even this century, but it's coming. as surely as dawn follows night. And when it happens, when that first spacecraft, whether it's a tiny light sail, no bigger than your hand, or an enormous generation ship carrying thousands of people, when it crosses that 1 light-year threshold and continues outward toward destinations we can now only dream of, it will carry with it the accumulated hopes, dreams, and achievements of everyone who came before. Every scientist who added to our understanding of the universe, every engineer who designed a better rocket or spacecraft, every astronaut who ventured into space and proved humans could survive there, every person who looked at the stars and wondered what might be possible. We're all part of this journey, even if we never leave Earth's surface. So how long does it take to travel 1 light year? With today's technology, far too long, 1,500 years or more. With the technology we're developing, perhaps decades or centuries. With technologies we can barely imagine, but that seem physically possible, maybe just years. But the real answer is this: we don't know yet because we're still in the process of figuring it out. We're still developing the capabilities, still learning what works and what doesn't, still pushing the boundaries of what's possible. And that's exactly where we should be, not at the end of the journey, but at its exciting, challenging, frustrating, inspiring beginning. The distance of 1 light year, impossibly vast as it is, represents not the limit of human ambition, but its next frontier. Every light year we eventually cross will make the next one easier. Every technology we develop will enable new technologies we can't yet envision. Every generation that contributes to this endeavor will make it more achievable for the next. We're building something that will outlast us, something that will carry humanity forward into a future among the stars. And that future, distant as it may be, starts with the work we do today, the questions we ask, the technologies we develop, the dreams we dare to pursue. The universe is vast beyond imagining, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, each potentially surrounded by worlds waiting to be discovered. Light years separate us from them, but light years are just a measure of distance, not of impossibility. We've already sent our spacecraft beyond the edge of our solar system into the space between stars. We've already taken the first steps. The next steps will be harder, requiring more time, more resources, more determination, but we'll take them. Because that's what we do. We explore, we discover. We reach for what lies beyond the horizon, even when the horizon is measured in light years. If you found this deep dive into the realities of interstellar travel fascinating, I'd really appreciate it if you could give this video a thumbs up and subscribe to the channel. And here's something to think about. If traveling 1 light year seems nearly impossible for us, what does that mean for any potential alien civilizations trying to reach Earth? We explored exactly that question in the video on the screen. Why is it impossible for aliens to ever reach Earth? Where we examine the other side of this equation, the Fermi paradox, the challenges any civilization faces in achieving interstellar travel, and why the same obstacles we've discussed today might mean that contact between civilizations is far rarer than science fiction suggests.